Section 1.4 is titled Continuity and One-Sided Limits. And the first thing we're going to talk about continuity several times in this section. The first continuity we're going to talk about is continuity at a point. So at a very specific one point in space, a function f is continuous at point C if the following are true. F of c is defined, okay, so that means that it exists. It's another way of saying it exists. It's actually a value. The second one is that the limit, as you're approaching it from both directions, notice that says x approaches c, so that means from both directions that exists. And the third thing is that while both of those things exist, they're also equal to each other. So you may be looking at that and saying, okay, but that sort of seems like you've said the same thing almost 3 times. So I'm going to draw you a couple pictures just to show you what could fail to happen if some of these conditions don't hold and why that would be not continuous. So to be not defined, one of the ways to be not defined is that you could have a hole in the graph. Another way is you could have an asymptote. Okay, with me so far? So if you have a hole in the graph or if you have an asymptote, I don't care if it's connected on either side or not, you have to stop drawing in order to continue the graph. You stop, you pick your pencil up, you start again. That's discontinuity. Okay? If you have an asymptote, it's even, worse, right? Something like this. Obviously had to pick up your pencil to draw it. So this can't happen and it be continuous. That's what this is saying right here. This can't happen. The second thing is, it says the limit has to exist. So you might be thinking, okay, well, isn't that sort of what you just already said? And the answer, of course, is no, but let me show you why. So let's say, for instance, the limit did not exist. Well, the limit does not exist when? What would have to happen for the limit to not exist? Right. The sides don't match up. So like one of the sides does something like this and the other side does this. Right? It's defined. I've got this closed-in circle right here. The function has a value, but the limit from both directions is not the same. And you clearly saw me pick up my pencil to continue drawing. That's discontinuity. This doesn't work. We can't do this. So you might say, okay, but doesn't that already take care of number 3? And the answer again is no. There's a third picture that I haven't exactly drawn yet. Actually, I drew it, but I didn't comment about it when I did it because I need one more piece on there. The function value exists. I got a closed-in circle. The limit exists, definitely. But they're not the same. Right? There's this sort of a jump in the graph at that one location. This would also be discontinuous. Okay, so that's what this continuity description is telling us can't happen. These kinds of images can't happen. All right, so this is at a specific point. Now we want to talk about on an interval in general, and the open interval is the one we're going to be most concerned with looking at. So a function is continuous on an open interval, so all the points between A and B, when it's continuous at all the points between A and B. It's like rocket science kind of definition here on this one. And if it's continuous on the entire number line from negative infinity to infinity, we call it everywhere continuous. Okay, what we're going to do in the next few problems is going to feel somewhat akin to what we were doing in section 1.3. So some of it you're going to be like, okay, isn't that what I already did before? That's true. We're just continuing the discussion. There is something a little bit different between this and what we did before. Can you tell what looks a little bit different between this problem and what we did in the last section? Yeah, it's got the one-sided part to it, right? The one-sided part to it doesn't actually change the evaluation of what we do. Okay, so that's what it's going to feel like we did the same thing already. And we did. Our attempt is going to be just like we did before to plug in the value. Okay? So as we plug in the value, if it doesn't plug in, that's when we have to be concerned about the fact that it has a plus or a minus. Okay? So are we able to actually plug this value in for x? We can. And what do we get? 1 over 16, right? Yeah. So this limit exists. says if it does not exist, we have to explain why. So is there a value, as you're looking at this particular function, the 1 over x plus 8, is there a value that would cause a problem for us? What would it be? Negative 8 would cause a problem. If we were told to find the limit as x approaches negative 8, that would cause a problem. So if this problem actually said that, we would have to do the explain why bit. What would be the reason why this limit would not exist if we did it for x approaching negative 8? Close. There would be an asymptote on this one. And remember, the way we decide if there's an asymptote or a hole is whether or not we're able to factor and eliminate the discontinuity. We're able to factor and eliminate the one that's causing problems. And this one's in very simple form, 1 over x plus 8. We wouldn't be able to reduce it, so it would be an asymptote. Okay, let's take a look at another one. This one is x approaches 9 from the left. What happens if we try to plug in 9 on this one? We get 0 over 0. And we encountered that happening last time too, didn't we? Do you remember what we did when we encountered 0 over 0 happening? There's two different things we could have done. The one that doesn't apply here is factoring. We tried to factor in and reduce something, right? And there's no factoring I can deal with on this one as such. I could factor this one actually, it would be okay. I'll show you that way to do it. But there's another one we dealt with that was a little bit more closely related to this picture of a function. Because it had a radical in it. What was that? Right, you got it. We rationalized the numerator by multiplying by the conjugate. So that's the one I was going to show you first. So let me show you that one, and then I'll go back and show you how it sort of could be thought of as factoring on this particular one because of the way it's set up. All right, so let's take a look at multiplying by the conjugate. What would be the conjugate of the numerator here? I hear you guys whispering, so somebody say it really loud for me. Okay, I would be okay with moderately loud.
Square root of x plus 3.
Thank you. Square root of x plus 3, and if I do it on top, I have to do it on bottom as well. Okay, we like the square root of x plus 3. And the reason we do is because conjugates, when they multiply, give us no inner and outer terms. That's not exactly true. They give us the same inner and outer term. It's just that they add to the 0 because their values are the same with opposite signs. So when I multiply the square root of x times the square root of x, I get x. My inside, my outsides, the same thing but negative of each other, opposite of each other, so they add to 0. And then my last terms, the negative 3 times the positive 3, give me minus 9. And that's exactly, of course, what I have in the denominator right here. And then I've got this square root of x plus 3 business going on still as well. So again, our whole goal was to be able to reduce the x minus 9 part because that's actually what's causing me problems to speak of. So my limit, and again, notice again, my limit is happening on every single step until I plug the 9 in. My limit as x approaches 9 from the left of 1 over the square root of x plus 3. Can I plug in my 9 now? I can. So now I have 1 over the square root of 9 plus 3, which is what? 1/6. Very good. All right, so just for fun, because I said initially that was not the natural approach, let me show you that we could, in fact, factor this if you thought about it that way. It doesn't work on every single conjugate one, but this one almost feels like factoring might make sense because I have x on top and bottom, and I have the minus 3 and plus 9 business, and there's those values going on the top and bottom. So what we could do is we could recognize, let me write this again. That when I have the square root of x minus 3 on top, and I have the value on bottom, it was x minus 9, that the square root of x could be written like this. It's factoring, it's not a quadratic, I get that, but the square root of what's in the very beginning term is square root of x, and the square root of what happens at the end is actually a 3, and you could do a minus and a plus. It's a variation of quadratic factoring is what it is. And depending on what kind of a college algebra or algebra 2 or algebra 3 math analysis kind of course, you may or may not have done something like this before. It works, it's pretty nice. It doesn't work on everything though, but it does work pretty cleanly if it does work. And so you can see if we did this route, we ended up with a lot less work, didn't we? Yeah, and I still end up with the exact same expression at the end that I had on the other one, and I end up with 1/6. So this would be another way you could do this one. All right, next problem is a little bit different. What causes this one to be a little bit different? What is it?
0 on the bottom.
Okay, if I tried to plug in 0, I'm going to get 0 over 0. That causes me a problem, definitely. But what about this makes it different than, say, the last problem? The absolute values is a little weird, right? I mean, like, you probably should, looking at this, think, well, I've kind of got x over x, but what do I do about the absolute value? You know what I'm saying? I mean, like, that's a little bit weird. What do I do? Well, this is a really good example of where it matters that we're looking as x approaches 0 from the left. It matters. So you tell me, what kind of numbers are we talking about if x is approaching 0 from the left? Negatives. Right? Okay, so just a real quick discussion about absolute values. It's going to feel a little bit funny, but if you have the absolute value of a negative number, what happens? It becomes positive. And a better way to think about it is what happens really is the sign changes. Right? It only happens when it's a negative number. The sign changes. So the easiest way to express the sign changes is to put a negative on the front of it. So we're going to rewrite this. And again, it feels funny to do so, but we're going to be rewriting this as negative x on top and x on bottom. Because if x is negative, then the absolute value is the opposite sign. So for instance, if you told me x is -5 and I plugged in -5 on top, the way it's written right now, will it be a +5? It will, because I've got an extra negative going on there, right? So the negative that I've put right here simply means that whatever x value I pick, I'm going to change the sign. And I'm only picking negative x values because it says x is approaching 0 from the left. Okay? Now you can actually reduce this in a way that makes sense. What happens when you have negative x over x? You get -1. And I'm going to draw you a picture of this in a moment so you can see how funny of a picture this actually looks like. What then is the limit as x approaches 0 from the left? Don't overthink it. What is it? It's just -1, right? It's just -1. The graph of this, in fact, why don't you grab your calculators out? You guys can see the graph on your calculators just as well as I can draw it. Go ahead and grab your calculators, and I would like for you to use, if you know where the absolute value feature is, if not, we'll find it together. I would like for you to put in y equals absolute value of x over x. Let me see if I can grab mine too. I think it's under the math button. Yes. So if you're in y equals and you hit math, your math button, and you arrow over to num, N-U-M, it says ABS parenthesis. So you can put that in. So in your calculator, you're putting in something like this. Looks like that in Y1. And then just take your window and just use the standard. Actually, you know what? Let's not, because it'll be a little bit too far zoomed out to see it very well. Just hit window and go from -1 to 1 on the x-axis, and let's go from -5 to 5 on the y-axis. So that's under window. Okay, is everybody's calculator cooperating with them? Excellent. So if so, you should be getting a graph that looks something like my red lines here. Does yours look like that? Yeah. And here's why. If the value is what we have, it's on the negative side, we're getting the -1. So we're getting a horizontal line down here at -1. What would have happened to this if we were approaching 0 from the right-hand side? What happens when you take absolute value of positive numbers? It stays positive, which means this numerator that I put in here as -x, I would put in as x. It wouldn't have changed signs. And what happens when I divide x by x? I get +1. So that's why you have +1 on the right-hand side. So the limit as x approaches 0 from the left is -1. The limit as x approaches 0 from the right would be what? 1, +1, right? This is the other part of the red line that I drew on the top over there. It's x approaches -1. I'm sorry, x approaches 0 from the right. It would be +1. So what would the limit be as x approaches 0? It does not exist, right? Because the two one-sided limits do not match up. It is discontinuous at x equals 0 as well, isn't it? It has a value, but it doesn't have the same one-sided limits, right? They don't match. All right, let's talk about these discontinuities then, because we've talked around them, but we haven't actually defined them this way. There are basically two types of discontinuities. One is called removable. This occurs when x can be made continuous by appropriately defining or redefining f of c. And you have non-removable, and this occurs when f cannot be made continuous by appropriately defining or redefining c. So I want to talk visually about what these actually look like when you have one or the other of them. A removable discontinuity is a hole in the graph. Oops. It may be a hole that's just left blank, or it may be a hole where they've taken the dot and they've put it too high, like I did on my last picture, right? So something looks like this, right? So this would be an example of where the function value needs to be redefined. We don't want the dot above where the open dot is. We want it to actually be filled in. That would be a redefining spot. This would be a place where we want to define the value. It's not defined right now at that open whole circle, right? So we want to define that it actually works there. Those are removable discontinuities. Any idea what non-removable discontinuities would be? There's a couple of them. Okay, we'll call that a jump, Evan. So if we had a jump in the graph, that is non-removable, right? I can't simply fill in the issue. It's too big. There's another kind of a jump in a graph. An asymptote, right? And in some sense, it's similar to a jump in the graph, but it usually is created in a very different way. So asymptotes are non-removable discontinuities. So you have something like that going on. So what our next examples are doing is we're going to take a look at some equations and to decide if we have removable or non-removable discontinuities. Okay? That's what we're going to be looking for. So really what we're looking for are asymptotes, holes, jumps, and graphs. Let me just make one comment here while we're here. Jumps and graphs happen with piecewise functions or absolute values. We saw it happen just a minute ago with absolute values. So if you don't have a piecewise function or an absolute value, you're not going to have a jump in your graph. Okay? That's usually the one that does not occur. It just doesn't happen very frequently. However, asymptotes and holes and graphs do. All right, so let's take a look at this one. The first one, the first thing it asks us to find is where f is not continuous. So at what value or values is x not continuous? At what? 6 works. 0 doesn't. What's wrong with 0? We have a 0 on the bottom, right? Okay, so it's discontinuous. Let me say it that way. At x equals 0. And what we want to decide is we want to decide if that discontinuity is removable or not. So what do you think? If I put in a 0 into this equation, am I going to get an asymptote or a hole? That's really what the question's asking me. It's an asymptote. What would have to happen for it to be a hole? Do you remember?
Is that where you have to be able to factor it out?
You got it. It's Hannah, right? Yeah. Hannah's right. That's the ones where we were able to do some kind of a factoring and it actually eliminated the problem spot. Or rationalization. We did one just a minute ago. We did rationalization. That would have created a whole kind of an issue in the graph, okay? So if we don't have the ability to factor this and simplify and make the whole go away, it's not a whole. Okay? I can't make this discontinuity go away, right? And because I can't, it's an asymptote. All right, so this one's an asymptote. It's also, let me say the way that they asked it, it is a non-removable discontinuity. And the reason why is because we can't, I'm going to say cancel out or reduce, you could use that phrase, cancel out the 0 occurring on bottom, the 0 occurring in the denominator. Hence, there's an asymptote. Any questions on that one? Okay, let's take a look at the next one. Same question. Which x values, for which x values, is this not continuous? So we need to do something before we can answer that question. What do we need to do? Factor. Yes, Nate, we need to factor. All right, so everybody factor this for me. How, and in particular, it's the denominator on this one. The numerator doesn't need any factoring. How will the denominator factor? Okay. Yep. Is everybody good with x minus 5, x plus 2? Okay. Before we go canceling, because I know that's what you're just aching to cancel. Before we cancel, we need to answer the first question, which is which values give us discontinuities? So looking at it in this form, what values give us discontinuities? Yeah, there's actually 2 of them, right? So this is discontinuous at x equal 5 and at x equal negative 2, both of them. And now we have to have both questions answered, which if either of them are removable or non-removable, okay? So now that we've sort of answered the first question, we can do the reducing, and we can find out that this reduces to 1 over x minus 5. So tell me then, since we listed it first, at x equal 5, what's happening? 0 in the denominator. Is it a removable or a non-removable discontinuity? It is non-removable for the exact same reason that the previous problem was, right? So at x equal 5, It's non-removable. And because you've already got the information written down, I'm just going to write same as above. Okay? It's the same reason that we already stated above. So what's happening at x equal negative 2? What is it? There's a hole in the graph. It's removable, right? And how do we know? Yeah, it's because we actually were able to remove the factor causing that discontinuity, right? We were able to cancel it out. So because we were able to cancel out the x plus 2, giving us a 0 in the denominator. Does that make sense? Yes, Marco. Mm-hmm. Oh, you said, I'm sorry, thank you. I think I said it and then I didn't write it. Thank you very much. X plus 2. Any questions on this one? Okay. The existence of a limit. If we have a function f and we have values c and l are real numbers, then the limit of f of x as x approaches is L, if and only if the limit from the left is L and the limit from the right is L. And we've talked about this already, but now this is sort of formally defined. This is what it takes for there to be the existence of a limit. Sometimes you'll see textbooks not even write the L in there. They'll just say the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x. They don't even use the L in there. Your book is wanting to make sure that you understand that L is a real number, not, say, infinity or something like that. All right, so we're going to do an example. This example is defined piecewise, so we do have the possibility that the two pieces might not match up, right? I mean, that is a distinct possibility anytime we have a piecewise function. But what we're wanting to do in this problem is we're wanting to find the value a so that that doesn't happen. We don't want the two sides to not end up at the same location. Okay? So how do we do that? Well, we're going to find the two one-sided limits and see if we can't figure out what a needs to be to make that actually happen. So the two one-sided limits are going to only potentially have problems at the place where we are changing the piece of the graph that we're on, namely x equal 1. Does everybody make sense with that? 1 is the concerning location because that's where my equation changes. So what we want to find is we want to find the limit of f of x, whoops, get that in the right location, as x approaches 1 from the left, and we want to find the limit of f of x as x approaches 1 from the right. Okay, so we'll do the left-hand side first, the limit as x approaches 1 from the left. Which equation is the equation that goes with the left description? Is it the 3x squared or is it ax minus 4? It's the ax minus 4, right? And the way we know is because it says less than 1. Okay, and then what we did on the last problems is exactly what we're going to do again. We're going to plug in the number 1 for x. So if we plug in the number 1 for x, what do we get? A minus 4. So is a still involved? Yes. We'll figure that part out in a minute, but for right now, a is still involved. All right, the other piece, we're supposed to find the limit as f of x as x approaches 1 from the right. Okay, well that's the other piece of the equation. So the limit as x approaches 1 from the right, and it's the other part of the equation, the 3x squared. So what value am I going to get if I plug now 1 in for x? 3. And according to the previous definition and the things that we've been talking about over and over again, the only way that this is continuous, that the limit exists, is if they actually meet up from the left and from the right. In other words, these two have to be equal to each other, or it's not going to work. So a minus 4 actually has to equal 3. What's a? 7. That's all there is to it. A7. Okay, we have a couple more parts about continuity that we're going to go through, and then we will get the last part about the intermediate value theorem next time. The definition of continuity on a closed interval. We did an open interval before, but on a closed interval. It says a function f is continuous on the closed interval from a to b, when f is continuous on the open interval from a to b, and the limit from the left-hand side, from the right-hand side of f of a, so as x approaches a of f of x is f of a, and the limit as x approaches b from the left-hand side is f of b. The function f is continuous from the right at a, left at b. All that this is saying is that if in fact you have endpoints, and these endpoints are at a and b, then the corresponding y value over here, f of a and f of b, if you're going along this curve from the right-hand side toward the value of a, you're approaching f of a. And if you're going along this curve from the left-hand side toward b, you're approaching f of b. It actually has closed-end endpoints. That's all this is saying. And then some properties of continuity. If b is a real number and f and g are continuous at x equals c, then the functions listed below are also continuous. So we kind of have already dealt with these particular descriptions before. We did it for limits, and now we're doing it for continuity. It makes sense that we have this definition for limits, this theorem for limits. We should have the same theorem for continuity because they're very related ideas. So if we have a function that's continuous and we multiply it by a number, the original function, continuous, the multiplication function, the scalar multiple is continuous, right? So if y equals x is continuous, then y equals 3x is continuous. If y equals sine x is continuous, then y equals 5 sine x is continuous. And it doesn't have to be whole numbers. They could be square root 3 times, cotangent of x or something like that. It doesn't have to be a whole number. If you add or subtract two functions that are continuous, you still have something that's continuous. If you multiply two functions that are continuous, you still have something that's continuous. And as long as the denominator is not 0, if you divide two functions that are continuous, you still have functions that are continuous. Okay, everywhere but where the denominator would be 0. That one's a little bit trickier because you can really get denominators equal to 0 pretty quickly. Any questions on this? Okay.